everybody. I want to use this video to talk about how to do two-sample hypothesis testing with proportions, which is a thing we haven't talked about yet. So let me go to the notes. All right, so two-sample hypothesis testing with proportions. So here's what we're going to do. The basic idea remains the same as in two-sample testing, both two-sample testing and proportions testing. So before we were testing, when we did one-sample tests with proportions, we would compare a proportion that a sample proportion to a hypothesized proportion and see if the sample proportion was far enough away that we could reject the hypothesized proportion. And we're going to do the same thing here, except instead of comparing one proportion to a number, we're going to compare two proportions to each other, two sample proportions to each other, to see if they were far enough apart that we think that the population proportions are not equal. So that gives us roughly the same sort of hypotheses that we had when we were doing difference of two means, right? So we've got, oops, what's going on here? What we've got is, in each case, is proportion one equal to proportion two or not, right? Either proportion one is bigger or proportion one is smaller, or proportion one and proportion two are just not equal to. So the way we're going to do that, there is a thing that we can do that we're going to do. It's analogous to pooled standard deviation from the means, from the means two-sample t-test. However, it's always true in this case. So we're just going to, like, there's not even an option to do not pooled, basically. So here's the idea. Remember before where we had S1 squared over n, or the square root of S1 squared over n was our sample standard deviation for one case, or for one sample. Here's what it would be for one sample proportion, right? Standard deviation of the sampling distribution for proportions. And so if we have two of those, we get this and this. And we're going to do the same thing with them that we did before, where we square the standard deviations, add them together, and then take the square root of the result, right? So I square this, and add them together and take the square root, and I get this thing. Now, here's the thing. Okay, so a couple things. Thing number one, we don't actually know what P and Q are when we're doing a confidence interval, but we do know what we don't know what they are when we're doing confidence interval. And in this case, our hypotheses are not going to be about what P1 and P2 each are, but rather that they're the same, right? The null hypothesis is going to be that P1 and P2 are the same. So that means that what we can do is a little bit of fancy math. So here, let me go ahead and do this. So I'm going to do a little bit of a math algebra aside. You can follow this if you want. You can also skip ahead in the video if you would like to. So here's the idea. What we're going to end up doing is this. Oops, sorry, that's a Q. We're going to be using that because we don't know what P1 and P2 actually are. However, we do know that they're the same. So here's the idea. Our null hypothesis is that P1 equals P2. That means that we start off the problem by assuming that this is true. And if that's true, then this thing, P1 prime, the sample proportion for P1, and P2 prime are both estimates of the same thing. And so the way you can get a better estimate is by treating those as though they are from the same sample effectively. And saying that, okay, well, a better estimate of P1 and P2, which are the same, a better estimate of P, right? So a thing we could say is this, P1 equals P2, which just equals P, right? There's not really two samples. It's really kind of one sample if the null hypothesis is to be believed. So here, let me, it is P. So what we do is we can take a weighted average of P1 or P1 prime and P2 prime. We can do this, P1 prime plus P2 prime. We can take a weighted average based on the sample size, right? So whichever of those is larger, we're going to trust more essentially, and we're going to trust them more in proportion to their the size of the sample, right? So it would be, to do that weighting, I would want to do N1 P1. Oops, I didn't leave myself enough room here. Sorry. N1 P1 prime plus N2 P2 prime. Oh, sorry, gosh darn it. Botching my my computer here. Plus N2 P2 prime, and then divide by the sum of the weights, N1 plus N2, right? And this would be our combined estimate of P, which we're going to call P sub C. Another way to see this, however, is that N1 P1 prime is this. So P1 prime is X1 over N1. And so another way to say N1 P1 prime, if I multiply both sides of this equation by N1, the thing that I get is that N1 P1 prime is X1. And so another way to write this formula here is this, X1 over plus X2 over N1 plus N2 is P sub C. And this is a more natural way to think of this. X1 plus X2 is the total number of successes. N1 plus N2 is the total sample size combined in both cases. So this is total number of successes out of total sample size. And that gives you what we can call P sub C. Now, what we're going to do with this is the following. We're going to use P sub C instead of P1 prime and P2 prime because P sub C is a better estimate of P, which is what we are using the P1 prime, or what we're using these primes for, is as estimates of P, right? That's what we're trying to do in this standard error. So what we end up with is something that looks like this. P1 prime Q1 prime over N1 plus P2 prime Q2 prime over N2. We are going to turn that into this. When I say approximately equal, really this approximately equal should be like a better estimate of the standard error is the following. So this is PCQC over N1 plus PCQC over N2. But the thing to do there is factor out the PC and QC, right? So I should really write this like this. PC, that's terrible. PC QC times 1 over N1 plus 1 over N2, square root of all that. This is the thing that we're going to use for our standard error. And I'll go back to look at the notes real quick. That's why we're doing this. Yeah, so digression over. That's why we're using this as our standard error right here. And so we end up with this Z statistic. It looks like this. Okay. That said, you don't actually have to know any of this to type into your calculator, which is really what I want you to be able to do. So let's we'll do this all the way through once. Oh, I should have written this differently here. I should say that the difference here. Let me go back to a whiteboard real quick. That the sampling distribution of P1 minus P2, so P1 minus P2 is approximately normal with a mean of 0, and a standard deviation of this thing. That is the standard error that we're going to be using for our hypothesis test. So let's go do a problem with this so we can see what it looks like. And so you can see that it's really not all that different. I know the math looks a little bit complicated there, but I think you will find that this particular problem is not all that hard. All right, so in the 14 stats classes I've taught before this one, which that's actually more now, I wrote this years ago, I had 418 students who received a final grade, 213 women, 205 men. Of the students, 142 of the women and 129 of the men ended up passing the class. So at a 5% level of significance, is there enough evidence to suggest that men and women pass my class at different rates? So let's notate everything here. Let's figure out what all of these numbers are telling us. So had a total of 418 students who received a grade, 213 women and 205 men. All right, so this is going to be N sub W and N sub M. 142 of the women and 129 of the men passed, so this is X sub W and X sub M. And I want to know if there's enough evidence to suggest that men and women pass my class at different rates. So I'm going to need a couple of things. I'm going to need to know what the proportions are, right? The proportion of women who passed, the proportion of men who passed, and P sub C, the combined proportion who passed. And then, so I need to calculate all those things, right? So P sub M, P sub W is going to be XW over NW, and P sub M is going to be, or excuse me, prime, is going to be X sub M over N sub M. Right, so the proportion of women who passed will be the total number of women who passed out of the total number of women. Proportion of men who passed will be the total number of men who passed divided by the, or excuse me, the number of men who passed divided by the total number of men. And P sub C is going to be the total number of people who passed out of the total number of people. So let's go to a whiteboard, write all that stuff down, and get calculating. So 142 and 129 out of 213 and 205. Okay. So I'm going to have, we're going to have some hypotheses. I'll write those in a second. They're pretty simple. Null hypothesis, alternative hypothesis. I just want to get all the numbers down while I'm thinking about them. So we have X sub W was 142 out of N sub W was 213. And we had X sub M was 129 out of 205. So P sub W, P prime W, excuse me, is 142 out of 213, which we'll calculate in a second. P prime sub M is 129 out of 205. And then P sub C is 142 plus 129. Well, I'll write it all down, right? 142 plus 129 out of 213 plus 205, which is 271 out of, well, 2 looks like a 1. This is 271 out of 418, or 18. Okay. So we can go calculate all that stuff up and then figure out what our sampling distribution looks like. So calculator. I didn't leave myself much room there, did I? Calculator. 142 divided by 213. There's the women. Oh, that's exactly 2/3. Interesting. And then the men, 129 out of 205. Right. So there's a difference in the proportion of the samples, right? 66.67% of the women passed, whereas only 62.9% of the men passed. So the sample proportions are slightly different from each other. The question is, are these different enough to make me think that women pass or that the overall pass rates, the overall population pass rates of men and women are different, rather than just the sample from me, right? Like is the overall pass rate for women in statistics different than the pass rate for men. So let's go back and write some hypotheses. So null hypothesis is that P sub women and P sub men are the same, and the alternative is that they're not. P sub women is not equal to P sub men. All right, so we know that the sampling distribution is, what's this P sub, let's say W minus M. We know it is normally distributed with a mean of 0, or at least we're proposing a mean of 0, right? That's our null hypothesis, is that there's no difference between the two. And a standard deviation of this guy. P sub C, Q sub C, times 1 over N1 plus, or N M W plus 1 over NM. Right, that is our sampling distribution that we're going to be using here. So let's go ahead and calculate that up. Square root of PC, QC, 1 over NW plus 1 over NM, and those were 213 and 205, and PC was 271 out of 418. Okay, it's a lot of stuff to type in here. So I've got square root of 271 over 418 times 1 minus that, right? So that's going to be 418 minus 271 is going to be 139 plus 18 is 157. So 157 out of 418. That's QC. Remember that Q is just 1 minus P. Times 1 over sample size for women was 213, plus 1 over the sample size for men was 205. And yeah, I think we're good to go there, right? Yes. There we go. 0.048 is our standard error. Okay, so let's go draw that. So this is my sampling distribution, or the standard deviation of my sampling distribution, which is the same as standard error. 0.0483. Let's go, yeah, 4 decimal places. So go to my whiteboard here. So this is this guy, centered at 0, because that's our hypothesized mean. And this is n with a mean of 0 and a standard deviation of 0. I forgot already. Let me go back and look at my calculator, sorry. 0.0483. 0.483. Now our actual difference was the difference in the proportions, right? So this is all the possible difference in proportions from the two sampling distributions. So let's go look at what our actual difference in proportions was. So that's in our calculator. There it is. So it was, so this was the women's proportion of success minus the men's proportion of success, 0.0374. So we're going to go put that on our sampling distribution. Here, 0.0374, right? So about 4% difference, 3.7%. And we want to know if this area plus this area, that's our p-value, right? The thing that I just shaded in is our p-value. So this plus this p-value. Here's the sum of those things. So to determine if we're going to reject our null hypothesis, I'm going to find those areas. So it's going to be 0.0374 up to infinity in the distribution, in this distribution. And we can see right away, without doing too much work, that this is not going to be big enough, right? This is less than 1 standard deviation, right? A standard deviation is 0.0483, it would be out here. This number is smaller than that. So this is going to be more than 32% for our p-value. But let's go ahead and do it anyway. in case that explanation didn't make a lot of sense to you. So we're going to do 2 times normal CDF. It was 0. Oh my God, I've forgotten everything. 0 point. I've forgotten everything. I'm sorry. I have to go back and look. 0.0374, 0.0483. Okay. 0.0374. 0.374. Oh my gosh. 0.0374. Upper bound of a lot. And this is 0.04. Shoot. Oh my God. I feel terrible having memory this bad. 483. Okay. 0.0483. There we go. Let's paste that in there. It's going to be pretty big, right? And so we get a p-value of 44%, so 43.8 or 43.9%. So that is, of course, not big enough or not small enough to reject the null hypothesis at all. Let's go back to my whiteboard. So this is about equal to 0.439. Right, so we're not going to reject the null hypothesis. Let's go make another page here. So don't reject the null hypothesis. This is not enough evidence to suggest that men and women pass my stats class at different rates. There you go. So that's the conclusion I want to come to. Like maybe they actually do pass at different rates, but this evidence doesn't show it. This evidence makes it seem like they probably passed at about the same rate population-wise. All right. So that is how you do this question. Sorry, I didn't go through these at all. I found all these, of course. Appropriate hypotheses, PC and QC. Those are the combined proportions, right? That was, where were we at here? That was these guys here, right? PC was 271 out of 418. QC was 1 minus this. So the remainder was 147 out of 418. Test statistic, I didn't actually bother doing that. I just did it on the normal distribution, which you can just skip if you have a normal distribution. We found our p-value, made our decision, and then I'm going to do the same thing again on the calculator. And you'll see that it's a lot easier. There's a lot less work to it. So yeah, let's do that. So calculator goes like this: stat tests 2 prop z. So we're doing a 2 proportion test here. So I'm going to make what do I do it in the order of women then men. So X1 was 142 women passed out of the 213 women who took the classes, and 129 men passed out of the 205 men who took the classes. And we're doing not equal to, so we calculate. And notice they don't ask for pooled versus not pooled. It's just always pooled here. Lo and behold, it's the same thing we got. They got a slightly different answer here because I did a little bit of rounding off in mine. But yeah, there you go. No big deal doing it this way. One thing I do want to point out, your calculator, like the rest of the world, calls these things p hat. Puts a little hat on the p. That is what everybody calls sample proportions, except your book. This is one of the big gripes I have with your book, is that they make up their own notation for things way too often. I don't know why they do it, but they do. I've used the notation that your book uses in the notes to go with the book, right? I wrote these notes to go with the book. So I tried to use the same notation, but if you take another stats class, they're not going to call it P sub C. They're going to call it P hat. They're not going to call it P prime. They're going to call those P hat as well. If you want to call them P hat, you're more than welcome to. I will know what you mean. If I accidentally call things P hat, please know what I mean. They're talking about sample proportion. But yeah, this is the standard notation for sample proportion, not the P sub C or P prime. They usually use hats. Anyway, here's P sub C is P hat here, and then we found these guys individually, or we found these guys individually as well. So anyway, I will expect you to be able to do this in your calculator. I don't expect you to be able to do it by hand, although knowing how it works by hand can help you understand what your calculator is doing. But the thing I really want you to concentrate on is what the numbers mean and what to do with them, not so much the formulas, which are a little bit complicated. Not to say that you couldn't understand something complicated, but I don't want the complication of the formulas or the complicatedness of the formulas to detract from your ability to understand what the numbers are telling you, which is the thing I really care about. So here you go. This is how you do it on your calculator. And I think that's really all I want to say about this. Yeah, I will go ahead and end the video now, and I will see you guys in the next one.